Hi students, welcome to Sunil's tutorial. I am Sunil Mirwani and today we will be doing this chapter of physics called as measurements. Right? Now let's go on to the definitions of measurement. First of all, in physics, what do we understand by physical quantity? Or what do we understand by quantity? A quantity that can be measured is called as a physical quantity. So how do I define a physical quantity? Any quantity that I can measure in some form, in the form of length, in the form of weight, or in any form. If I can measure a physical quantity, then that quantity that particular quantity is called as physical quantity. Next, what do we understand by measurement? Measurement means comparing a physical quantity with some accepted standard. For example, if I say that I want 5 kgs of tomato, what is 5 kgs of tomato? 5 kgs of tomato is 5 times 1 kg of tomato. Right? That means here your accepted standard is 1 kg. I want 5 times the accepted standard. So what am I doing? I'm comparing a physical quantity with some accepted standard. This is called as measurement. So what is measurement? Measurement of a physical quantity is the comparison with some accepted standard, right? That is called as measurement. Next, now when I say 5 kgs of tomato, the word 5 kg is made up of two words, 5 which is called as magnitude and kg which is called as unit. So when we talk about measurements, when you measure anything, a measurement is made up of magnitude and unit. So what is a unit? A standard which is used for measurement is called as a unit. Anything that is used for measurement is called as unit. Okay, so an accepted standard or a standard used for measurement of physical quantity is called as unit. Now, can anything and everything become a unit? No. You have to have certain requirements for a good physical unit. First of all, in order for anything to be a unit, a good physical unit should be of suitable size and well defined so that it can be easily reproduced. It should be of a suitable size so that a person who wants to do measurement should be able to carry it from place to place. It should be well defined. The same unit should be present all over, right? It should be invariable. That means the magnitude should now not vary with place and time. Whether I do the measurement here or I do it anywhere, the physical quantity should be measured in the same manner. It should be easily reproducible. Only then can I have a proper physical quantity, physical unit. Fine, do we get this thing clear? So thus, I can say a unit, that is a standard which contains definite, durable, stable and easily reproducible amount of same kind of physical quantity when compared with another physical quantity. So how do I define a unit? A unit is defined as a standard which contains definite, durable, stable, easily reproducible amount of some kind of physical quantity with which other similar physical quantity can be compared. Right? Once we have unit, there are two different units that exist. One is called as the SI unit and the other is called as the CGS unit. The SI unit is also referred to as the MKS unit. Right? So a physical quantity can be measured in meter, kilogram, second system, or it can be measured in centimeters, gram, second system. These are the two systems which are used. Okay. Now when we talk about units, units can be further classified into fundamental units and derived units. Right? What do we understand by fundamental units? Units which cannot be defined with the help of other units are called as fundamental units. Units which cannot be defined with the help of other units are called as fundamental units. For example, length. I cannot use any other units to define length. Mass, time, electric current, luminous intensity, the amount of brightness, temperature, and the amount of substance. That is, in chemistry you studied mole, 1 mole, right? So there are 7 fundamental units. These are the 7 fundamental units. What are fundamental units? Units which cannot be defined in terms of any other unit are called as fundamental units. Fine. The 7 fundamental units are length, mass, time, electric current, luminous intensity, temperature and amount of substance. Fine. Next, what are derived units? Units which can be derived with the help of fundamental units are called as derived units. So if I can derive the unit for a physical quantity using fundamental units, then that would be called as derived units. Fine, do we get this? Now, what do we understand by dimensions? Dimensions of a physical quantity is defined as the power to which the fundamental units are raised to obtain a physical quantity. I'll explain this, guys. First, let's understand the definition. Dimensions of a physical quantity is defined as the power to which fundamental units are raised to obtain 1 unit of that physical quantity. Now, I'll explain this to you with the help of an example, guys. Let's see this. For example, let's find out the dimensions. Let's first find out the dimension of, say, speed. Now we know that speed is nothing but displacement upon time. Speed is nothing but displacement upon time, right? We measure displacement in terms of length. We measure time in terms of seconds. Now, if I have to write dimensions of speed, first of all, dimensions are always represented between square brackets, right? Now, when you are writing dimensions, first thing you have to do is write MLT, right? In speed, you are not measuring mass. You have length in the numerator, so L is going to be raised to 1, and you have time in the denominator, so time is going to be raised to -1. So the dimensions of speed are m0, l1, t minus 1. m0, l raised to 1, length is in the numerator and it is measured only once, therefore l1. Time is in the denominator and measured only once, therefore t minus 1. Next, velocity. Velocity is nothing but displacement upon time. Therefore, what will be the dimensions of velocity? The dimensions of velocity will be mlt. You do not have mass, so m raised to 0. You have displacement which is measured in terms of length. You have it in the numerator, therefore L raised to 1. You have time which is in the denominator, therefore T raised to -1. Right? So this will be the dimension of velocity. Next, acceleration. How do I find out the dimensions of acceleration? Acceleration is nothing but velocity upon time. But velocity is nothing but displacement upon time. Therefore, I can say that acceleration is displacement upon time square. Therefore, the dimensions of acceleration will be mlt. m0, you are not measuring mass. You are measuring displacement in terms of length, so L1. You are measuring time square in the denominator, therefore -2. So the dimensions of acceleration are m0, L1, t -2. Next, momentum. Momentum is defined as mass into velocity, right? But velocity is nothing but displacement upon time. Therefore, dimensions of momentum will be nothing but mlt. You are measuring mass, so m raised to 1, displacement in the numerator l raised to 1, time in the denominator t raised to minus 1. Fine. Next, force. Force is defined as mass into acceleration. Right? Mass into acceleration. Acceleration is displacement upon time square. Therefore, dimensions of force will be mlt, m1, l1, t minus 2. Those will be the dimensions of force. Next, work. Work is defined as force into displacement. Right? Force we just found out is nothing but mass into displacement upon time square. That is force into displacement. Therefore, the dimensions, first thing you have to do is convert everything into fundamental quantities. Dimensions of work will be mlt, m1, l2 because displacement into displacement, and t minus 2. Right? Next, power. Power is defined as work upon time. Right? Work is defined as mass into displacement square upon time square, right, into time. Thus, I can say that power, dimensions of power is mlt, m1, l2, t minus 3. Fine, do we get this thing here? Next, let's see pressure. Pressure is defined as force upon area. Right? Force, we just found out force is nothing but mass into displacement upon time square. Area is nothing but length square, so therefore I can say area is nothing but displacement square. Displacement and square gets cancelled, therefore the dimensions of pressure are mlt, m1, l minus 1 because displacement is in the denominator, and t minus 2. Right? Do we get this thing here? Next, density. Density is nothing but mass upon volume. Straightforward this is. So the dimensions of density are going to be mlt. Mass is 1. We know that volume is L cube. So L raised to minus 3 and T 0. Volume is in the denominator, therefore minus 3. Fine, do we get this thing clear? Next, impulse. Impulse is given by the formula force into time. But force we know is nothing but mass into displacement upon time square into time. So time and square will get cancelled. So in which case my dimensions of impulse is going to be m1 l1 t minus 1. Those are going to be your dimensions of impulse. Next, torque. Torque is nothing but force into distance. Force is nothing but mass into displacement upon time square into distance. That means you are going to be measuring distance twice. So the dimensions of torque will be m1 L2 t minus 2. Why L2? Because length is measured twice here. So this is how to find out dimension, and these are the dimensions of certain physical quantities. Fine, do we get this? Question: why are we learning dimensions? Right? Let's find out the use of dimensions. The use of dimension analysis. First, where do we use dimensions? Dimensions are used to verify the truth of a physical equation. First, to verify the truth of a physical equation. That's the first application of dimensions, right? And how do we do that? We verify the truth of a physical equation by using the principle of homogeneous dimension. By using the principle of homogeneous dimensions. That means in a physical equation, if the left hand side and the right hand side has same dimensions, then the equation is correct. For example, let us consider the equation V is equal to U plus AT, kinematical equation, right? Now, where V stands for final velocity, U stands for initial velocity, A is acceleration and T is time, right? Now let's find out the dimensions of V. Velocity is displacement upon time, so m0 L1 T minus 1. U, initial velocity. Velocity is displacement upon time. A is nothing but displacement upon time square. AT, right, is displacement upon time square into time, m0 L0 T1. So when you multiply this will become m0 L1 T minus 1. Now if you look at all the physical quantities that are involved in this equation have the same dimension. The dimensions are homogeneous. m0 L1 T minus 1, m0 L1 T minus 1, m0 L1 T minus 1. Since each term of the equation has same dimension, therefore the nature of each term is same, hence the equation is dimensionally correct. Since each term of the equation has same dimensions, right? Therefore, the equation is dimensionally correct. Fine, do you get this? That is the first application of dimensions. Next, where else do we use dimensions? Dimensions are used to determine the conversion factor between the units. Second application, to determine the conversion factor between units. That's the second application of dimension analysis. They are used to determine the conversion factor between units of the same physical quantity. Units of same physical quantity. For example, if I want to find out the relationship between SI and CGS unit of force, I want to find out 1 dyne is equal to how many newtons, or 1 newton is equal to how many dynes. Let us assume that 1 newton is equal to X dynes. I want to find out the conversion factor between the SI unit and CGS unit, right? Newton is the dimension of force. The dimension of force is m1 L1 T minus 2. So I can say that m1 L1 T minus 2 is equal to X times dyne is also the unit of force, m1 L1 T minus 2, right? Now in this case this is going to be m1. m1 means this is going to be kilogram. L1, that is meter, into time square, time raised to minus 2, is equal to X times grams into centimeter into time raised to minus 2. Time raised to minus 2 gets cancelled on both the sides. Now 1 kilogram can be written as 1000 grams, 1 meter can be written as 100 centimeter, is X into gram into centimeter. Gram and gram gets cancelled, centimeter and centimeter gets cancelled, so X is 1000 into 100, X is 10 to the power of 5. Therefore, I can say that 1 Newton is 10 to the power of 5 dynes. So thus, I come to know the conversion factor between various units, right? Now the third use is to derive a relationship between various physical quantity. To derive a relation between various physical quantity, right? Now let's see this. How do I find out the relationship between various physical quantities, right? Now, for example, if I have an equation, I want to know what is the relationship between various physical quantities in the equation. For example, let's consider kinetic energy. Now, kinetic energy experimentally can be found out that kinetic energy is directly proportional to mass and kinetic energy is directly proportional to velocity. Now I need to know a mathematical equation. I need to know a physical equation that gives me a relationship between kinetic energy, mass and velocity, right? So I can say that if there is a relationship between them, then the dimensions of kinetic energy should be equal to k times the dimensions of mass raised to x and the dimensions of velocity raised to y, right? Where k is a numerical constant, x and y are the powers to which mass and velocity are raised, which have to be determined. Now let's write this. Energy. Energy is the capacity to do work. Work is force into displacement, and let's find this out separately. Kinetic energy. Energy is nothing but force into displacement. Force is nothing but mass into displacement upon time square. Therefore, the dimensions of kinetic energy is going to be mass into displacement upon time square into displacement. So that is going to be nothing but m1 L1 T minus 2. Okay. From equation, I can say that if the equation is dimensionally correct, then the dimension of kinetic energy should be equal to k times the dimension of mass raised to x and velocity raised to y. Therefore, I can say that m1 L2 T minus 2 is k times m1 L0 T0 raised to x. Velocity is displacement upon time square. Velocity is displacement upon time. So this is m0 L1 T minus 1 raised to y. Therefore, you could say that m1 L2 T minus 2 is k times m raised to x, L raised to y, T raised to minus y. Since the equation is dimensionally correct, I will say equating like terms, I'll get m raised to 1 is m raised to x, therefore x is equal to 1. Similarly, L raised to 2 is L raised to y, therefore I can say that y is equal to 2. Hence, I come to know that kinetic energy is k times mass raised to 1 and velocity raised to 2. Once I have this, then experimentally I can find out the value of k by experiment. K is going to be equal to 1 by 2. Thus, the equation is derived that kinetic energy is half mv square. That's how you derive an equation using dimensional analysis. Fine, do we get this thing clear? Next. Okay, we'll stop here for the day. We'll continue with this in the next lecture. Thank you very much.